So dear judges, we are from Tsinghua University and our project is a CNT-polypyrrole core-shell sponge and its application as a highly compressible supercapacitor electrode. This is the outline. After a brief introduction, we will mainly talk about the fabrication of the core-shell sponge and its supercapacitor application. Nowadays, in facing the increasingly serious energy and environmental problems, people pay special attention to the new type of green renewable energy. And meanwhile, the study of energy conversion and storage technology has become a research hotspot. The new energy storage technology is considered to be a strategic technology to support the popularization of renewable energy applications. And it also has important applications in industry and daily life. It has become one of the key to solve the energy and the environmental problems. Among the various energy storage devices, there's a unique supercapacitor. It's a kind of electrochemical capacitor with a high energy density, and its performance is between the conventional capacitor and the battery. It has unique properties. High power density, 10 to 100 times higher than battery, and its fast charging, long cycle life. These are useful for its applications. For example, in the field of electrochemical, in the field of environmental friendly vehicles, the high power density can help to meet the power requirements of electric cars at the start, acceleration, and climbing. And in the field of renewable energy storage, supercapacitor can achieve weak current charging. This can improve the energy utilization efficiency. And electrode material is a key for the supercapacitor performance. Nanotechnology has opened up new frontiers in material science and engineering to develop unique electrode. In particular, carbon nanotubes have high surface area, suitable pulse distribution, excellent conductivity, and stability. These features all suggest their promising potential for supercapacitor application. And nowadays, supercapacitor based on CNT have attracted extensive research attention. There are two main hotspots. One is the performance improvement, and another is the development of flexible electrode. But the CNT-related flexible electrodes are mainly stretchable or bendable. But compressible electrodes have seldom been investigated, although compression is one of the most influential factors on the performance of flexible supercapacitor. So based on such situation, we proposed our research project. We plan to develop a compressible electrode based on CNT materials and explore its supercapacitor application, and we want to obtain a high performance. Next, I will introduce our unique CNT PPY core-shell sponge. The fabrication starts from the CNT sponge synthesized by chemical vapor deposition. This is a schematic for the CVD system, and this is a figure. It shows a block of the CNT sponge. It's light, porous, and flexible. And more important, the porous structure can provide a general platform for functional materials deposition. So we introduced PPY, polypyrrole, a typical and environmental friendly conductive polymer usually used to enhance the supercapacitor performance. This is a process. We directly immerse the CNT sponge in PY solution and to absorb PPY monomers on the CNT surface, and then through electropolymerization, the PPY monomers will cross-linked into a uniform PPY layer and results in this core-shell sponge. From figure, we can see that after PPY deposition, the sponge can maintain its original shape, and it can be compressed to large strengths without breaking or collapse. And even after 1,000 compression cycles, it can recover to its original volume. And from the SEM and TM images also show well-controlled PPY deposition. A uniform PPY layer wrapped each individual carbon nanotubes and form the core-shell configuration. It can maintain the porous structure and reduce the charge carrier transfer distance, and also the CNT network can transport the charge carriers efficiently. And other characterizations, SPS, Raman, TGA, also confirm the successful deposition of PPY. And more important, the thickness of PPY layer can be well controlled in our method. By control the PY solution concentration and the absorption period, we can control the thickness range from 5 to 60 nanometers. Next, we explore the supercapacitor performance of this sponge. We assembled a prototype 2-electrode schematic supercapacitor. The left is a schematic and the right is a assembled capacitor cell. The main characteristic of our design is that the in-situ compression can be performed by the two clamps here. Yeah, by the two clamps here. Sorry. And we first investigate the impact of the PPY loading. This is the three curves of the sponge with different PPY loadings, and this is the specific capacitance. From this, we can see that PPY deposition leads to really high current density and high capacitance. And what's more, the PPY loading is not a small matter. Moderate loading of about 58% leads to a maximum capacitance about 335 farad per gram. This is a real high level in this field. And next, we explore its compressible electrode performance. Figure A shows the supercapacitor under in-situ compression. And the capacitor shows similar three curves under compression compared to the original state. And the sponge electrode under high degree compression, it can retain more than 90% of the original capacitance, and it shows significantly improved volume normalized capacitance. We further investigate the performance under cyclic compression, and we find that PPY coating can reinforce the sponge structure. From figure A, the compressive stress strain curve, we can see that at the same strain, the CNT-PPY sponge shows higher stress than the CNT sponge, black line. And after 1,000 compression cycles, we can see that the deformation here is smaller than 5%. The sponge shows excellent structural stability. And the three curves before and after cyclic compression are quite similar. So the sponge has a stable capacitor behavior and cyclic compression. And to conclude, first, we presented a rational design and fabrication of CNT and PPY co-shell sponge. A PPY layer with controlled thickness was coated uniformly on individual CNTs, resulting in a co-shell configuration. Second, we further demonstrated its application as highly compressible supercapacitor electrode, and we obtained excellent performance. For example, it can retain more than 90% of original capacitance, and after 1,000 conversion cycles, it can maintain a stable capacitance, and the maximum capacitance can as high as 335 farad per gram. And third, the sponge can serve as highly compressible and robust electrodes for supercapacitors and many other energy devices. Our research will benefit the development of next generation advanced supercapacitors with tolerance to hardish conditions, such as mechanical concussion and compression. And the last acknowledgements, we thank TECO Technology Foundation and Future City and New Energy Interest Group of Tsinghua University for the fund support. And we thank the supporting labs from Peking and Tsinghua University, and thank all my team members and advisors. That's all. Thank you.
Thank you. So the innovation that you have focus on the compressible electrodes. Right?
Yeah.
So your capacitance actually increased after the compression.
Yeah.
How about before? Before the compression, is there any gain in capacitance?
Thank you for your question. Do you mean that the capacitance before our...
Your CNT PPY or CNT without PPY?
Oh, yeah.
The capacitance with uncompressed, not compressed.
This the left figure shows the comparison between the silicons compressed with bare CNT and the CNT PPY sponge, and the right is calculated specific capacitance. We can see that without PPY, the porous CNT sponge only has the capacitance is within 25. Exactly, it's 17 farad per gram. And after PPI deposition, the highest capacitance can reach about 300. And about your another question, maybe this figure can explain. And before and after the compression is stable, the capacitance are the same, almost the same.
Okay, how about your capacitance compared to other materials like active carbon?
Yeah. Thank you for your question. It's really hard to maybe the usually used supercapacitor electrode is active carbon, and this porous compound tube. The main characteristic of our projector is about the comparison, and we must adapt that the performance of CNT is sometimes lower than active carbon. So maybe that is must we will work on in the future to further improve the performance, because due to the time limit of our project, we just work on it for half a year, and we still have lots of work to do.
So can you think of any applications where your compressible electrode has much higher benefit?
The application fields, yeah. Maybe we.
What kind of application that needs this high compressible electrodes?
Oh, thank you for your question. We think that in this young project we just develop a fabrication process, but we just want to find out some application fields for this compressive supercapacitor electrode. But you know that in lab situation, and we just need some help to find a practical design for this device, and this is our future plan to optimize the device design towards a practical application. Thank you.
Okay, thank you.
谢谢。
CNT-polypyrrole supercapacitor. First, let me show some experimental details on how we synthesize the CNT technologies. And this is the schematic of the system and the structure. This is actually what is mixed up. During the process, first we check the device and see all the furnace. Almost at this place, we see all the furnace. And then we heat it to about 860 degrees Celsius. And after that, we inject the carbon source. The carbon source is the chlorobenzene and mixed with the catalyst precursor. I forget how to pronounce it. In Chinese, it's 二毛铁. And at last, we collect the CNT sponges from the substrate. The substrate is the quartz sheet. Because using that, we can endure the high temperature.
And the picture just shows the block of CNT sponge. It has unique three-dimensional well-controlled porous nanostructure. And another enormous advantage is that the CNT sponges have excellent mechanical properties and structural stability. And we can know from the picture, and no matter how we deal with the CNT sponges, it also keeps their stability and they are very compressible and flexible. And the CNT sponges also have ferroelectric conductivity. It favors faster high. Besides, CNT sponges have relatively high surface area, and based on such properties, CNT sponges provide a general platform for functional materials composition. You use the horizontal CVD, not the vertical CVD. Yes. Horizontal. Yes. And how can guarantee the surface property is good? Surface property. Then make a demonstration, right? Because you go this way. Should you have the spin? The tube, yeah.
The quartz sheet is made like tube, like this.
Yeah, I know. Usually the CVD is vertical.
Yeah.
Yeah, vertical. But you use horizontal. Therefore, you carry a gas go like this way. And how can you guarantee the position? The quality of this in this is equal to this. Usually it become thicker. In the end, it becomes thinner. The thickness.
Usually it is the mass is very usually sometimes it's big and sometimes it can be thin. But usually we can find the right positions to place these causes sheets, and it will about girls such thick sponges.
Yeah, I think you need to provide this product specification. Product specification in terms of your physical, chemical properties.
So this is
okay. Also, you have to provide some performance. Okay, compare with others. Products. Give the list, the table. Yeah.
So what's the function of this?
So that's just give the data. You didn't put it in the table.
After that fabrication process, you can just get some samples like with my hand. It's very light, soft, and most importantly, press very flexible. And you can press large strength or breaking or clasping, and very fast. And we can focus on its mechanical properties. And we see from here that the higher loading of PPY is the higher level of stress it can sustain, and the smaller deformation sample develops. And this is a measurement process. We put two sponges here, filter paper beside it, and this is two slabs. And we just in that platinum wax just around the box here, it just acts as a collector. And this method is made by ourselves, and it's quite convenient and it's easy to control. And this because our program is very limited.
现在我们
这是后续有一个应用，
主要是看
最开始
Later, we
前2年都是在做
produce other electrolytes.
这种 CNT 的东西
We improve its performance. The electrolytes now we use are
博士班都在搞，弄完以后就是你这个有什么特别的，所以这个特别的时候要从 green chemistry 去看 green chemistry， 再从绿色化学，就这边
But how about the added value of the